Hi, my name is Arjun, and I'll be presenting our work on adjoint nonlinear ray tracing. In our world, there are many materials where light rays traveling inside them bend continuously. Examples include mirages, mixed drinks, and gas flows. In rendering, we simulate the appearance of these materials using nonlinear ray tracing. To better understand this, we can start by approximating such a material with layers of constant refractive index. We can use refraction to calculate how light deflects at the interface within the material, forming a piecewise linear ray. As we increase the fidelity of this approximation, we calculate more refraction events. If we take the limit of increasing piecewise constant approximation to this underlying refractive index, we end up with a material that has smoothly varying refractive index. Then, light will continuously curve through the medium rather than refract at discrete interfaces. This is what we mean by nonlinear in nonlinear ray tracing. And rendering these materials is a well-studied problem in graphics. But what we're interested in is the inverse rendering problem. What spatially varying refractive index parameters generate a target image given a particular light source? Our chosen method for solving this task is to use differentiable rendering. There's been a considerable amount of work on this topic in the past few years, but in the context of nonlinear ray tracing, the only available technique until this point is to calculate gradients using reverse mode automatic differentiation, or autodiff. Unfortunately, naively using autodiff requires an enormous amount of memory. For example, when optimizing a volume designed to display Albert Einstein, autodiff uses more than 5 gigabytes of memory for a single iteration within the optimization. Instead, we developed a method for calculating gradients that uses an order of magnitude less memory. And consequently, we're able to double the resolution of the volume and increase the quality of the resulting image in the optimization with little increase in our memory usage. So let's talk about how tracing works. Consider a volume with refractive index eta defined at each point x inside the volume. To model how rays travel through this medium, we define a ray as starting from a point x0 and having initial direction v0. Geometric optics gives us a set of equations that tells us how x and v evolve as the ray travels through the medium. What results is a nonlinear, curving path through the volume. To simulate this on a computer, we need to discretize these evolution equations using some time step parameter we get to choose. Once again, we start with an initial position and direction. We look at the refractive index value, eta, located at position x0, and then update the direction v0 according to the discretized equations. Then we travel in a straight line along the direction for a distance equal to our step size, delta t. Once we reach this new point, we look at the underlying eta value again and update v. We then repeat this process of updating x and v until we reach the boundary of the volume. In the inverse problem, we have a target point that we want our ray to reach at the end of the tracing procedure. Our inverse problem is formally the minimization of the difference between the endpoint xf and the target point x hat. We solve this problem using a gradient descent approach, which requires obtaining the gradient of the loss function with respect to refractive index, eta. Existing techniques for calculating this gradient use autodiff. This works by recording the history of the tracing procedure I just described, storing the whole trajectory and intermediate quantities in memory. Autodiff calculates the desired gradient by applying the chain rule as it traverses this computation graph backwards. However, let's say we need to take more steps along the trajectory, maybe because the volume is larger or we want a more accurate simulation. Then the graph that we will store will need to be larger to accommodate the extra steps taken. This means we cannot run the simulation for an arbitrary number of time steps since we will eventually run out of memory. Our main technical insight is that we don't actually need to store this computation graph, nor do we need to remember the trajectory of the ray. If we instead run the same tracing procedure, using our final position and the reversed final direction, we can actually recover the original path. And since we know what the computation looks like at each step, we can recover the graph that autodiff would have stored, meaning that we can perform the same graph traversal autodiff does without needing to store any graph in memory. In the paper, we show additional details on how to formally derive this backward tracing procedure using the adjoint state method, we derive continuous backtracing equations and show what discretization schemes are suitable for this backtracing procedure. I won't go into these details, and instead invite you to take a look at the paper. Now, I will show some optimization results that we produced using our method, both of which focus on continuously refractive media used to create so-called gradient index or GRIN optics. The first such result is the replication of the Lüneburg lens. In 1944, Rudolf Lüneburg proposed a GRIN optical piece that holds the property that rays of light coming from one direction will focus to a diametrically opposed point on the surface of the lens. This is true from all directions. He gave an analytic refractive index profile that achieves this property. But suppose we don't have an analytic solution, and only a description of the geometric properties of the rays. If light is entering from a certain direction, it should exit the lens at the antipodal point, x target. This should be true of all of the rays entering the volume with the same direction. Our loss, then, is the sum of the distances between these exit positions of these rays and x target. We solved this optimization problem using a multi-resolution approach, starting from a resolution of 3 cubed and going to a resolution of 129 cubed. Once it converges, it successfully focuses the rays to the target point. And if we look at a slice through the lens of our optimized refractive index in purple and compare it against the analytic solution from Lüneburg in orange, we see that the profile is almost perfectly reconstructed. Next, I show a setting where our optimization procedure can be applied to improve performance rather than just replicating an existing lens. In fiber optics, fibers are designed to transmit light between 2 points, and in the center of these fibers is a core that uses gradient index material. A common profile for GRIN fibers is the parabolic profile. In it, light travels along sinusoidal paths. However, light rays entering the fiber at different distances from the center of the fiber travel different path lengths, causing the wavefront to deform. This is known as modal dispersion. What we would like is for light rays entering at different distances from the center to all focus at focal points throughout the fiber, therefore minimizing the amount of dispersion the wavefront sees as it propagates through the fiber. So we can formulate an optimization problem in which all light traveling in the fiber should pass through a focus point, the loss being the distance from the closest point along the ray to the target point. When we run the optimization procedure, we end up with a profile that is able to focus all of the light at discrete points throughout this fiber. And if we look at a cross-section at one of these focus points, we can visually confirm that the optimized profile does perform better than the parabolic profile. And looking at a focus point later in the fiber, we say that in both cases, focus degrades, but the optimized profile still performs better. With our method, we can design other kinds of GRIN optics, such as multi-view and light field displays, as well as solve some reconstruction tasks. Please refer to our paper for details on these experiments. Our paper and the code used to perform these experiments are all available online. Thank you for your attention.